Well, hello. Now let me tell you about one of the most frustrating subjects I encountered in my undergraduate studies. Lagrangian mechanics and the principle of least action. Now to set the scene a little bit, imagine a young math and physics student fresh out of high school. The first classes in the first semester were about special relativity and set theory. On the one hand, we learned about a mind-boggling alteration of Newton's laws that messed with our very understanding of space and especially time. And on the other hand, we learned about the very fundaments of mathematics and the deceptive nature of infinity. At the time, I was of course already aware of the strange world of quantum mechanics and very eager to start learning about it. But a quick glance at the curriculum showed that first we would spend a semester on classical mechanics, using the book Analytical Mechanics. Now, leafing through that book before class made me really feel like we're going to just regurgitate Newton's laws in the dullest way possible, focusing entirely on boring minutiae. On the other hand, the teacher for the course was Erik Verlinde, a pretty renowned string theorist, for crying out loud. Perhaps it would have been a good early indication that maybe this topic is actually worth more than I gave it credit for back then. At the time, however, let's just say that I didn't enjoy it much, especially at the point that we started considering Lagrangian mechanics. And I know I wasn't alone in this. It was like making things super difficult with all kinds of random stuff. Well, it seemed the main goal is to show that there's another wacky way of finding Newton's laws, which we already knew about. Now, if you happen to have any experience in the field of physics, or in fact many other fields that use the same mathematical formalism, you will know that I was very wrong. Lagrangian mechanics and the principle of least action are immensely powerful and versatile ways of formalizing mechanics. Now, what I think that went wrong in my undergraduate course is that there was such an emphasis on the operational understanding of the theory and very little attention for the intuition. So in this video, I'd like to show you how Lagrangian mechanics is such a uniquely intuitive way of mathematically formalizing mechanics.
First of all, let's consider what the objective of our theory should be. If we look at the time that the theory was developed, the problem was something like, suppose I shoot a cannonball from point A to point B, then what is the trajectory that this cannonball will take? Now, actually, we're usually more interested in other so-called boundary conditions, like not giving the starting and ending locations, but the starting location and starting velocity. But for this explanation of the intuition, let's remain with that first situation in mind. For instance, the ball could follow this trajectory. But a priori there's no reason to assume it wouldn't take this trajectory instead. If the ball goes from point A at time 0 to point B at time 1, then mathematically what we are interested in is the path gamma, which is a function from the unit interval from 0 to 1, to the configuration space. The configuration space is the space of all possible configurations of the system, in this case, locations of the cannonball. So in the end, the trajectory is just a function from that interval to three-dimensional space. Of course, there are also situations with some other configuration space. For instance, we can consider a rigid pendulum. We take a weight, attach to a rod, and pin it to swing in a particular plane, like you would find in a grandfather clock. Then the configurations of this system are given by the location of the weight and can only be on some point on a circle centered wherever the pendulum is pinned. So we can have this configuration, or this one, or this one. So the configuration space is just a circle. And trajectories are just paths on the circle that can be doubled back on, of course. In fact, the cannonball could also have doubled back, although that would be quite unexpected in that situation. And we can like, what if we fire two cannonballs from points A1 and A2 to points B1 and B2 respectively, at the same time? Now you may think this necessitates two configuration spaces. However, we'll make do with one, albeit a more complicated one. A point in this configuration space will be a point in a 6-dimensional space. If we would introduce coordinates, we can specify the location of a cannonball using 3 coordinates, x, y, and z. So we can specify the location of 2 cannonballs using 6 coordinates, 3 for each ball. A trajectory then is still a function from the interval to this 6-dimensional space. Now you may think this is a bit silly because we could just describe the 2 cannonballs separately, right? But there are situations where it really is better to describe things in a unified manner like this. Like, what if we consider a double pendulum? So not just 2 pendulums, but a system where one of our pendulums is attached to the other one. Here is a possible configuration of that system. The configuration of the system is not just provided by the location of the second weight, since there are several different configurations where that second weight ends up in the same place. So we really have to provide the locations of both of the weights somehow. For the first one, nothing has changed. It still lies on that circle we saw before, so its location is provided by an angle, as before. However, the possible locations of the second one are highly dependent on the locations of the first one. For each of the infinite locations that the first weight can be in, there is a different circle that the second weight can be in. To deal with this dependency, which we often call coupling, we have to do something smart. Instead of giving the actual location of the second weight, we just give its location relative to the location of the first weight. So in the end we give 2 angles. One is the angle of the first weight around the place that it is pinned, and the other is the angle of the second weight around the center of the first weight, wherever that may be. Now in fact this means that the configuration space is actually the surface of a torus. The first angle refers to the horizontal circles in the torus, as you can see here. And the second angle refers to the vertical circles in the torus, as you can see here. So here you can see a general trajectory of this system. Note, it is just a path in the configuration space again.
Okay, so in that book in undergraduate class, this stuff was explained as what are called generalized coordinates, and the way they explained it was really kind of boring, which didn't help. And there are more complicated examples we could look at, like, for instance, Euler famously had to dive into configuration spaces of ships. But for now, let's stick with these relatively simple examples so we get an intuition of the principle of least action. And I'm cutting away from all the animation stuff here because I want to point out the main takeaway today, which is the basic underpinning of the principle of least action. Namely that you can find out which path is actually the physical trajectory of your system by just assuming that there exists some value associated to each path, which we call the action, and that this value is the most extreme for the physically correct trajectory, right? So if we have our point A and our point B, there are going to be many trajectories, like so, from point A to point B, comma 1 here, comma 2, comma 3, and one of them is going to be our actual trajectory. And so what we're going to do is we're going to say, well, just associate some number, let's say r of gamma 1, and we have r of gamma 2, we have r of gamma 3, and we could maybe call this like the realness. How real is that path actually? And then we take the realist path. That's the one that actually happens, right? Well, so that is really the basics of the principle of least action. It's really intuitive, I think. Just nature's trying to extremize something. And what that actually is that it's trying to extremize, that's what we'll have to find out somehow. Now, in the way that this was discovered and how people came about this, they actually didn't go for this realness and they didn't maximize either, but rather they went for minus this thing essentially, or at least something that's minimized, right? So, and then the action S of one of these paths is some function that when you minimize it, that's the path that is actually physically correct, right? So this is the thing that only long after that class clicked with me, is that because we're so tied up with all this operational stuff, is that the main principle is really just to assume that the trajectory that nature chooses or that actually happens has to minimize some quantity, something. Now to figure out what that quantity is, let's make some straightforward assumptions.
In fact, let's first look at a simple example by considering a discrete configuration space. Let's consider a configuration space which is simply a 4x4 board numbered, as you can see on the screen. Actually, this is the game board of the game of Snakes and Ladders, also called Chutes and Ladders sometimes. The objective of the game is to roll a die and make it from square 1 to square 16. However, there are also ladders, shown in green, and snakes, shown in red. When you land on a ladder, you automatically climb up, and when you land on a snake, you automatically fall down. In this example, we've also discretized time in a way, so we move in a sort of turn-based manner every time we roll the die. In this case, the configuration space is simply the board, and a trajectory is some sequence of squares on the board. Actually, by rolling the die, we would introduce randomness in this situation, and this would make it a very nice example to explain the principle of least action in a quantum mechanical context, like quantum electrodynamics. However, today we remain classical. So to remove the randomness, we assume that we simply roll a weighted die that always comes out at 1. Here is a simple trajectory in the system. This is not a physically correct trajectory, of course, because we are ignoring the snake, and the snakes and ladders are our stand-ins for the law of physics in this situation. Now, how do we decide what the action of this path gamma is? Well, one straightforward thing to consider is that we might split the path up in two parts, gamma 1 and gamma 2, shown here in purple and yellow. It seems reasonable that if gamma 1 is the right path from its start to end, and gamma 2 is the right path from its start to end, then so is gamma in total. In fact, the other way around also seems to make sense. Gamma should only be the right path if, whenever we split it up into smaller paths, each of those is also the correct path from its starting point to its ending point. For the action, this means that the value it associates to gamma should simply be the sum of the value it associates to gamma 1 and gamma 2. That way we can guarantee that if the action of gamma is minimal, then so is that of gamma 1 and gamma 2, and vice versa. Now if we then split up gamma 1 and gamma 2 in two parts again, and continue like that, we will eventually end up splitting up gamma in pieces which cannot be split further, because they just go from one square to the next. So we can define what the action should be by stating what the action is for each move from one square to another square, and then stating that the action of any path is given by adding up the action of these building blocks. Then to get an action that is minimal for paths that follow the rules, we can simply say that going from one square to the next has action 0 if it follows the rules, and 1 otherwise. So if we're on square 11, each square we move to next would add the black number written on it to the action. Note that there's just 1 0 because there's always just one legal move. If we were on square 12, it would look like this. So the action of this path is actually 1, since we ignore one rule. The action of the actual correct path will be 0, and thus minimal by definition. Now, of course, this example is quite far from the physical systems we just talked about. But this actually shows that the principle of least action can actually be applied in a far wider range. And in fact, it is. This example also gives us a hint about how to define the action for the physical systems, which we'll see next. Let's revisit the pendulum system we saw earlier. The configuration space was just a circle, and in fact we don't really need to think about the underlying reality anymore. We just want to figure out how to generalize what we just learned about actions to the continuous case. As before, we have 2 points, A and B, and we want to know the trajectory between them. So for instance, we could find this yellow path, or this purple one. We will choose between them by computing the action. So how do we do that? Well, again we could try to zoom in and consider smaller and smaller subpaths. But in this case, we will never arrive at an undivisible path. So we'll go for the next best thing instead of summing up the actions of actual subpaths. We consider that our continuous trajectory is built up out of uncountably infinitely many infinitesimal pieces, each contributing some action density. So instead of summing up all the actions of actual undivisible pieces of path, we integrate this action density. Now what I've been calling the action density for now is what is actually called the Lagrangian. This provides a number for each infinitesimal piece of path, which we can then integrate to obtain the full action. So what exactly is an infinitesimal piece of path? As you can see, as we zoom in more and more, the configuration space starts to look more and more like a straight line. This means that if we zoom in more and more and more, all we are eventually left with is the location of the point we are zooming in on and the direction of the path at that point. So an infinitesimal path is just a point in configuration space and a velocity in that point. Indeed, the Newton-Laplace principle also states that you should be able to describe the evolution of a system using only the location and velocities of all of its particles. This provides us with what is called the phase space. Each point in the phase space is just a point in the configuration space and additionally a velocity that the system could have in that point. For instance, for this example, the configuration space is a circle and the phase space is an infinite cylinder, since for each point on the circle you could have any velocity in either of the two directions. So in the end, the Lagrangian is just a function on the phase space, and integrating the Lagrangian gives us the action. And now think about it, we got to this really from just asking something very basic, namely that correct paths should split up into correct paths. Continuing this way, we can actually also say a lot about the Lagrangian itself from such fundamental ideas, at least in certain idealized situations. First, let's start in the ideal situation of just one particle and nothing else at all in the entire universe. We are kind of in the cannonball situation, so the configuration space is just three-dimensional space, and the phase space is just six-dimensional space. 3 for the position, and 3 to give a vector that indicates the velocity. So our Lagrangian will depend on location, velocity, and time. The first fundamental idea is that time is homogeneous. That is to say, if there's nothing around that makes the next moment different from the previous, then the system should look the same independent of time. Since in this idealized setting there just isn't anything that could tell us the time, we can therefore assume that the Lagrangian also doesn't depend on time. The second fundamental idea is actually that space is also homogeneous, so it looks the same everywhere, and therefore the exact location should not factor into the Lagrangian either. In fact, you can see this principle in action here. It may look like the ball is moving, but really it might just as well be the camera that is moving. The homogeneity of space makes it so you simply cannot tell. So since the physics should not depend on where we are observing it, the Lagrangian should not depend explicitly on the location either. All it can depend on is velocity. However, even this dependence is minimized by the third fundamental idea, namely that space is also isotropic, meaning that it looks the same in every direction. This is made evident here because again it is impossible to distinguish whether the arrow and the sphere are moving or actually the camera is moving. Again, since the physics should not depend on in what direction we are observing it, the Lagrangian should also not depend on the direction of the velocity. So all that remains for it to depend on is the length of the velocity vector, or in other words the speed of the particle. Here we consider the absolute value, so the square root of the square of the speed. This is relevant because if you ask a physicist to provide the Lagrangian in this situation, they will give something only slightly different. Namely, they will take the square of our Lagrangian and multiply it by 1/2 and the mass of the particle. But to be fair, this Lagrangian will also perform quite well as only based on certain fundamental assumptions about the nature of space and time. You can already kind of see that Newton's first law would follow from this Lagrangian. Indeed, integrating this Lagrangian from start time to end time is like integrating the location of the path, and this is minimized by the shortest path between the starting and ending location. So suppose we make the situation a little bit less ideal by adding another particle. Let's assume that the first term we found from the more idealized situation is still worth something, so that we start with that term and then add something else, some function v. Now actually let's do the physicists a favor and write it like they would, using the actual kinetic energy terms and a minus in front of this function v, which is the potential. Again, since we are coming at this from a fundamental angle, these seem like arbitrary things to do, but of course a lot of empirical work has also gone into this topic. Now again, time is homogeneous, since we just have two permanent particles, and let's also assume for the sake of clarity that this new term in the Lagrangian does not depend on the velocities explicitly. So the entire velocity dependence is in the kinetic energy terms. Again, if you look at the two balls moving in unity, it is impossible to tell whether the balls are moving or whether the camera is moving. So the homogeneity and isotropy of space are again making it so that the potential function v cannot just simply depend on x1 and x2 in any form. However, note that if the distance between the two balls changes, we can say for sure that it's not the camera that is moving, but it is actually the balls. This means that the potential can only depend on the distance between the balls, which is expressed as the length of the vector pointing from one to the other. In particular, you can hopefully see how this can lead to Newton's third law, since the distance from ball 1 to ball 2 is of course also the distance from ball 2 to ball 1, only pointing in the other direction. Again, the details here are for another time, when we'll discuss the Euler-Lagrange equations in all their glory. But think of how cool it actually is that you can reason both the general form of the Lagrangian and Newton's laws from just fundamentals like homogeneity and isotropy of space. In other words, from relativity of location and direction.
Yeah, so hopefully you actually got something out of that. To me, it's really some piece of physics and mathematics that really made me think about how these things work. You know, like yeah, that things that we come about empirically sometimes, or through some kind of thought experiment, that they really all fall into place in the end. So in the end, it really works when you just think about, okay, something is being extremized. If you think about it hard enough, you involve your symmetries and basic assumptions about the world, then you arrive at Newton's laws, which I think is a wonderful thing and a nice place to end this video. Cheers.